Hello there. I thought I could create a short little video here explaining the function of a dielectric inside of a capacitor, just on a very basic level for our physics class. I've got some pictures here on the screen that show how dielectrics are incorporated into the actual construction of different types of capacitors. And you could think of them as serving two main purposes. The main one is it greatly increases the capacitance of a capacitor by a certain factor. We'll call its dielectric constant, and I'll explain that part in just a moment. And it also allows the two metal plates, the electrodes as we call them, to be really, really close together without them actually touching. Because if the two electrodes touch each other, well, then you just have a big hunk of metal. You don't really have much of a capacitor at all. So if we put a thin layer of a dielectric in between them and then make a sandwich out of it and roll it up real tight, then we can squeeze a lot of capacitance into a very small space. And back when electronics were shrinking and trying to fit everything into a small circuit board, that was very functional. And now we've taken capacitors even to a smaller level, the micro level, and that's kind of where electronics are going now. So let me explain how this gets incorporated into physics problems that you might be doing with dielectrics in capacitors. The primary way that the dielectrics get incorporated into your physics problems is outlined here in the center with the red box. When a capacitor that has air separating the electrodes is replaced by an identical one with a dielectric in there, then the capacitance of that capacitor is increased by a factor that we call kappa. They use a regular K in this symbol here. It's actually the Greek letter kappa. And the diagram here shows the difference between an air-filled capacitor versus a dielectric-filled capacitor. And the main difference here is in the dielectric, you have these polar molecules that when there's charge on the capacitor, polar molecules will end up aligning themselves, and they align in such a way that the negatives get attracted, or the negative parts of the poles, the dipoles, get attracted to the positive plate, that's the upper plate here, and the positive part of the dipole gets attracted down, in this case, to the lower electrode. And so the net effect here, and I'll circle it in blue, is that if you look at all of the charge that is now collected near the top plate, it includes not only the free charge on the metal electrode, marked with the pluses, but you also have up right against it some net negative charge due to the polarized dielectric. And in a similar way, down on the lower plate, you have the free electrons from your capacitor plate, but you also have a net positive charge in the dielectric. And so the dipoles themselves create a small opposing electric field. They call it here the electric field of the polarization, that effectively reduces the electric field that had previously been in the air-filled capacitor, which we describe over here on the left where the air is. So the electric field now, due to the whole arrangement, what they call the effective electric field, is lower than the original electric field by this factor known as the dielectric constant kappa. And since the capacitance is related to how much electric field you can build up on a particular capacitor, again, the easiest way to describe it is we just increase the capacitance by this factor kappa. So you notice it here in this expression for the capacitance on the right, whereas the capacitance on the left does not include that. For air, we just use a dielectric constant of 1. Everything is kind of compared against that. Now let's look at two practical ways that we might see the effect of this smaller electric field. Here's a diagram showing on the left an air-filled capacitor, just a typical parallel plate capacitor shown, and this is just a representation of one. And we have previously charged it up with some charge they call Q naught, and the capacitance we could find by epsilon sub naught times A over D, and those would be the the surface area of the plate, each plate divided by the distance separating them, and we have some voltage built up across that from those charges. What we see here in this box that I circled, that's just a voltmeter registering how much voltage is across those plates. Well, look here on the right, when we put this dielectric in there, because the electric field effectively is now reduced, and the potential difference is directly proportional to that electric field, what that means is the potential difference is also reduced by that factor. So in this case here, if you just look at the meter, it seems to be at half scale, whereas over here it was full scale. So perhaps we have a dielectric with a constant of 2. So when you have the charge on the plates, and notice here the charge is now stuck in place. We have no way to move it because we removed the battery or whatever got it there in the first place. All we're doing here is registering the potential difference. Then that charge cannot change. See here we got Q naught on the plate still, but because the capacitance has gone up, that makes the potential difference go down. And I'm using here an important relationship, QVC. I bought it from a shopping network on the TV, and because Q cannot change, that means if the C is going to go up, V is going to have to go down proportionally. That's what we call an inverse relationship. Now let's look at the other way that we can introduce a dielectric into a capacitor. I've taken the previous figure and I've altered it a little bit, you can kind of tell maybe, and we still see the same thing on the left side. We've got an air-filled capacitor which has a capacitance of C naught, a charge on it of Q naught, and I'm going to mark here the potential difference of V naught that actually got the charge on there. Now the difference here is we're going to leave the battery hooked up, which means now we have the ability to move some charge around. So if we introduce the dielectric in here, that orange material, then the charge is actually going to end up increasing to a new value. So I'm going to get rid of this Q naught. We don't have that anymore. We have some new Q value, and that's because we cannot change the potential difference across that capacitor since we're still hooked up to the same original voltage or potential difference that we had before. So now when we look at the QVC relationship, it's applied a little differently. We're still increasing the capacitance by introducing the dielectric, but because we cannot change the voltage in this case, or the potential difference, then the Q has to increase proportionally to the capacitance increase. So again, using the maybe the same dielectric we had in the last example, we will now have twice as much charge built up on these capacitor plates as what we had originally with the same potential difference. So if you remember that the capacitance is just the ratio of how much charge we can build up for a given potential difference, it doesn't really matter whether we increase the Q as we did here, or on the previous page we decrease the voltage. We still end up getting that same ratio that the capacitance value has with the dielectric. So now there's some other examples that I'm not going to go through here that are good exercises for you, and that would be, for example, what if we have two series capacitors or maybe two parallel capacitors, and then we introduce a dielectric into just one of them. And that requires a little bit more analysis than what I've given you here, but I think you've got the tools now to be able to apply that, and you can probably find examples of those in your textbook or some other reference that you can use. So hopefully that's helpful for you, and if you need more help, of course, you can find me in class.